Hello and welcome to Loughborough Power Company. Today we'd like to talk about the construction of overhead transmission lines and in particular wooden 11 kV overhead poles. I'd like to pass you over now to our erection specialist, Alan.
Hi, I'm Alan. Today I'm going to give you a brief overview of a typical 11 kV wooden pole arrangement. As you can see, there are many different pole arrangements. There is a terminal pole, a spur pole, a sectional angle, an intermediate pole and a terminal pole or H-pole arrangement. The H-pole arrangement is usually used for larger transformers. A smaller transformer will normally go on a single terminal pole. As we can see in this picture, we have a typical H-pole arrangement, a cross beam with the transformer sitting on it, and in this particular picture, a cable running up the side, a termination onto the overhead line. In order to connect the cable onto the overhead line and the transformer onto the overhead line, we use a series of cables off each line section. Those line sections are called bowls. Here we have a couple of pictures where bowls are used in different applications. This picture here shows a cable running up the pole to a termination, end termination, where we can see the cables off the end of the termination onto the line. These wires here are the bowls. Here, the wires coming off the line again are the bowls, and this is an ABSD, an air brake switching device, where supply runs down one side of the line and can be isolated via a switch, and we can see the switch in this picture here. This switch will generally be operated with a long insulated handle from the ground and will open to create a break in the circuit. Here we have a series of pictures showing different line connections. The picture on the right shows a line coming in from the right and going out on the left. In order to connect the electricity from one point to another, we use a loop connection. The loop is insulated at the top via the pin insulator. Moving on to the second picture, we have a line coming in from the right and then a cross section going out in a different direction. In order for the electricity again to be connected from one line to the other, we use a series of wires. They again are called loop connections. As we can see, this wire is larger than this wire over here. This is the main line and is supported by these stays coming down at the angle there. These stays will hold the line in position and would normally have another set of stays at the other end of the line to counteract the force. On this particular picture we can see additional stays here from the spur line counteracting the forces from the line going off at the angle there and the angle going off there. I'll now hand over to my colleague Alan Barry, our Senior Erection Specialist.
Hi, I'm Alan, the Erection Specialist at Loughborough Power. Today we're going to have a brief introduction into... As my colleague Alan has already mentioned, there are many different types of pole. Today we're going to look at an intermediate type pole. Firstly, we will look at the dimensions of a standard wooden pole. Poles vary in height between 8 and 14 metres. Depending on the height of the pole, the diameter can vary between 145 to 160 millimetres. And generally the pole will be 1.4 metres underground. Depending on the location of the pole, an anti-climbing device may be fitted. These come in a number of formats, whether it be a single metal piece or barbed wire. To extend the life of the pole, it is treated with creosote. This is to prevent it from rotting. As you can see, there is 3 pin insulators at the top of the pole. These insulators insulate the line conductor from the pole. They're shaped in such a way that the rain runs off them, keeping the underside dry and non-conductive. They can be made out of glass, ceramic or porcelain.
Hi, I'm Anathan and I'm a contractor for Loughborough Power with detailed knowledge of the skin effect. The skin effect is the unequal flow of current through a conductor. As you can see from this drawing here, the red highlights how much current is flowing through the cable or the line, and it's a lot higher on the outside edge of the conductor. The The skin effect is caused by the interaction of magnetic flux within the cross-section of the overhead line. Within the center of the shape, you're affected by a lot more layers, meaning that there's a lot more interaction between magnetic flux, causing a lower flow of current. The opposite is true with the outer surface, which only meets the air, and so has less interaction with the other layers of the cross-section, resulting in a higher current flowing through the cross-section. The problem with the skin effect is it leads to a lot of wasted material within the cross-section. There's no current flowing through the center, and so there's a lot of extra weight you have in your cross-section which isn't actually being used. A further issue is the effective resistance of your overhead line is increased. There are several methods we can use to reduce the effects of the skin effect. What we have here, the delta represents the skin depth. This is the depth carrying the majority of the current, and this is what we want to increase to reduce the effect of the skin effect. This phenomena is more prevalent within larger conductors, so there are several methods we could use just within this vein. Having a hollow cross-section reduces the amount of wasted material, as you have the area in the center, which isn't carrying much current, missing, and so you have less weight and less expense on your overhead line. A further method of reducing the skin effect is to change the frequency of the alternating current. As you can see from the diagram here, the blue represents the amount of current flowing within the cross-section. With the larger frequencies, there's a very small amount of current flowing, very small skin depth, compared with the smaller frequency, 60 Hz, which is a lot closer to what we actually use for our alternating current, has a much larger amount of current flowing and a much deeper skin depth. The material used also affects the skin depth. For example, skin depth is directly proportional to the resistivity of the material. There's a special material sometimes used in overhead lines called Litz wire, which is shown here. The Litz wire is braided and constructed in such a way that it causes the magnetic flux to interact and give a much more efficient use of material because the current is constant throughout the entire cross-section. Finally, I'll hand you back over to our Managing Director, Dave, to conclude the presentation.
Finally, I'd like to talk about surges. Surges on the 11 kV overhead system have two main causes, external and internal. External causes are mainly lightning strikes onto the network. Internal surges have various causes. These include earth faults, sudden changes in load on the system, and also switching of large capacitor banks. One method of surge control is via a surge arrestor. These work by diverting a lightning strike to the ground rather than passing it to sensitive equipment. You can see here a system without a surge arrestor fitted, where the cable joins onto the transformer feeding the house. If there was a lightning strike, it would hit the main line and the large voltage would travel through the transformer, possibly causing a failure. You can see on this system a surge arrestor is fitted, so if there was a lightning strike, it would hit the main line, but then the large amount of voltage would flow through the surge arrestor and then to ground, avoiding any faults or failures. Surge arrestors work by having multiple layers of MOVs. These are metal oxide varistors. In normal conditions, the MOV acts as an insulator. Thus, the voltage will flow through its normal path through a transformer or any other equipment. If a large voltage spike occurs, the MOV acts as a conductor. This thus diverts the large voltage to earth, and hence you would protect any sensitive equipment. Another method of shield control is via utilising a shielding line. Shielding lines can be run either as a single or dual supply line, and they protect cables within roughly 30 degrees of the shielding line. The main disadvantage of a shielding line is that it will only protect against external surges. For the most effective protection against surges, both surge arrestors and shielding lines should be utilised to protect against internal surges and external surges. This concludes our presentation on overhead transmission lines. Thank you for listening, and goodbye.